The recovery of Yakovlev Yak-1 from Polonets Lake represents a strict study in environmental isolation and materials engineering. In December 1942, a fighter aircraft came to rest on a frozen lake surface. It was still recognizably complete, but the damage pattern would only matter once the aircraft could be examined. It was upright enough to be tempting, yet entirely inaccessible. The boundary was not terrain, but geometry and ordnance. A localized tactical stalemate placed the airframe exactly between opposing front lines. To understand how a recoverable fighter becomes a delayed forensic operation, we must first trace the thermal failure that forced it onto the ice. The sequence initiated during a combat engagement over the Demyansk area. The aircraft, piloted by Michael Kudryashov, absorbed incoming fire from opposing German fighters. The critical damage was not a catastrophic structural failure or flight control severance. The projectile struck the ventral coolant radiator. This specific component failure dictated the immediate fate of the aircraft due to coolant depletion mechanics. Liquid-cooled aviation engines like the Klimov M105P operate within a highly restricted thermal envelope. When the radiator matrix sustains a ballistic puncture, the system loses internal pressure and the coolant rapidly evacuates into the slipstream. Without a fluid medium to transfer heat away from the cylinder banks, the engine experiences immediate, exponential heat buildup. The internal metal components begin to expand beyond their design tolerances. The pilot faced a rapidly closing threshold. Continued operation without effective cooling could lead to overheating and seizure at any time, and the longer he stayed airborne, the smaller the margin became. Continued flight back to a secure airfield was no longer a realistic assumption. The procedural requirement was a mandatory transition from combat maneuvering to an emergency landing profile before the engine failed, or the cooling loss made control of the situation impossible. Kudryashov had to identify a clear, flat surface and shed altitude immediately. He selected the frozen expanse of Polonets Lake. This forced an operational decision regarding aircraft configuration. Deploying landing gear over a natural, unverified ice surface could introduce severe risk if the wheels broke through crust or struck an ice ridge. But the exact cockpit selection cannot be reconstructed with the certainty of a checklist. What the recovery evidence makes clear is that the undercarriage collapsed during the forced landing, so the safest wording is to treat this as a forced ice landing rather than a fully documented gear selection. He brought the fighter down onto the ice, the lower structure absorbing the first impact. The aircraft slid horizontally across the low-friction ice plane. It dissipated its kinetic energy entirely through the friction of the fuselage underside against the ice until it came to a complete halt. The steel tube structure of the fuselage maintained its integrity, preventing the airframe from disintegrating. The pilot executed the forced landing perfectly. He successfully extracted himself from the cockpit, traversed the exposed lake surface on foot, and returned to Russian lines. The Yak-1 was now a tempting winter recovery target. The ice offered a possible working surface, and Soviet teams attempted to reach the valuable fighter for recovery. However, the geographic placement of the forced landing created an absolute denial zone. The lake was situated directly in the center of a contested front. Opposing forces held the adjacent shorelines. When Soviet salvage crews attempted to move onto the open ice, they were immediately targeted by German crossfire. The flat expanse of the lake offered zero cover. The operation required time, rigging, and stationary targets, all of which were impossible under direct line-of-sight fire. Simultaneously, German ground units recognized the intelligence and material value of the downed fighter. When they attempted their own recovery operations from the opposite shore, Soviet forces pinned them down with the same lethal geometry. The physical distance to the aircraft was negligible, but the operational environment locked the airframe in place. Throughout the winter months, the aircraft remained abandoned in the center of the kill zone. The structural condition of the mixed material fighter was largely unaffected by the ambient freezing temperatures. The recovery operation was simply suspended, waiting for a shift in the tactical lines. But the tactical stalemate would soon be outpaced by an absolute environmental schedule. The flat, solid surface currently supporting the aircraft was a temporary seasonal condition. How did an aircraft stranded on solid ice become a deep water recovery target? The next phase was governed by the season. The ice had kept the aircraft suspended, but only as a temporary condition. Now, the shifting environment would dictate the next phase of the investigation. In the spring of 1943, the ambient temperature in the Demyansk area shifted, initiating a catastrophic change in the support surface. Ice platform collapse is a measurable structural failure governed by thermal loading and material fatigue. As seasonal temperatures rise, the ice sheet degrades simultaneously from solar radiation on the upper crust and warmer water currents flowing beneath. The crystalline structure loses its tensile strength, transforming from a rigid plate into a fractured, yielding surface. The static mass of the aircraft remained constant, but the upward resistance of the ice decreased exponentially until the shear stress finally exceeded the structural limit of the frozen surface. The aircraft broke through the weakened crust. As it descended, water filled the engine bay, cockpit, and fuselage spaces, and the fighter settled on the lakebed in about 59 feet or 18 meters of water. On the lakebed, Polonets Lake provided a highly specific preservation matrix. For 48 years, the airframe rested in profound isolation. The cold, freshwater environment slowed many forms of biological decay and corrosion compared with warmer, oxygen-rich, saltwater exposure. The lake acted less like a perfect vault than a slow-motion conservation chamber. Unlike a saltwater ocean environment, this freshwater lake lacked the aggressive chloride ions that actively strip electrons from metal surfaces and accelerate severe galvanic corrosion. That chemistry slowed the damage without stopping it. However, the environment was not entirely static. The slow chemical exchange between the fresh water and the mixed material construction of the aircraft was ongoing, setting the conditions for future forensic analysis. The site remained completely undisturbed until October 1990. The military front lines that originally blocked recovery had dissolved decades ago, leaving only the technical challenge of heavy salvage in an aquatic environment. Locating the aircraft was straightforward based on historical positioning, but extracting it from 59 feet required careful load management. The primary constraint during underwater lift operations is the trapped weight of water and sediment inside the airframe. The thick mud of the lakebed creates a powerful suction effect against the belly of the aircraft. Overcoming this breakout force without tearing the fuselage apart requires extremely slow, controlled tension on the lifting cables. Once the breakout began, the lift through the water column remained deliberate and measured. As the aircraft broke the surface of the lake, the team had to avoid turning the flooded airframe into an overloaded hanging weight. Water, silt, and mud inside the fuselage and wing structure had to drain before the suspended load could be carried safely. Recovery crews often have to manage this clearing process while the aircraft is suspended, a highly vulnerable phase of the operation. Only after the internal water evacuated could the aircraft be safely swung onto the recovery barge. The extraction from the lake was a complete operational success. The physical structure was secured and returned to dry land. However, bringing the airframe out of the water immediately created a new forensic problem. The recovery team had secured the physical artifact, but establishing its exact historical provenance required analyzing factory stamps, heavily obscured by time. Once lifted from the lakebed, how could investigators establish the exact identity of the airframe when its own factory markings presented a contradiction? The physical extraction of an aircraft from a lakebed is only the first phase of a forensic recovery. Securing the artifact immediately triggers a rigorous identification protocol. Upon initial inspection of the airframe, investigators encountered a severe evidence contradiction. The welded steel tube fuselage retained a clear, heavily stamped manufacturer number, read as 8188. However, this designation did not align with known operational loss records for that specific sector. The primary identification anchor appeared to be a dead end. This contradiction is a common procedural hazard when analyzing mass-produced military hardware. During rapid wartime manufacturing, sub-assemblies like fuselages, wings, and engine mounts are often built in different factories or different departments, each applying its own internal tracking codes. The military supply chain, however, only registers the final, top-level aircraft serial number assigned at the end of the final assembly line. The frame stamp therefore pointed to a factory process, not directly to a combat loss record. To bridge this gap, investigators had to rely on archival evidence triangulation. Archival evidence triangulation bypasses an ambiguous primary stamp by using verified subcomponent serial numbers. Those numbers are then checked against surviving maintenance logs, supply manifests, and factory acceptance ledgers to reconstruct the host aircraft. To execute this method, the recovery team had to locate and clean secondary components that survived the decades of immersion. Scouring the airframe, they extracted the primary armament, one Schwach 20mm cannon and two SKAS 7.6 2mm machine guns. Because weapons are controlled, precision manufactured items, their serial numbers are stamped deeply into hardened steel receivers. The 3 gun serials were legible enough to support the identification despite the long submergence. Furthermore, investigators located fragmented numerical markings painted on surviving cowlings and stenciled onto ammunition boxes. With the weapon number secured, historians initiated a deep search through surviving Russian archival material. The objective was to find documentation that linked those exact 3 gun serials to the recovered aircraft. The archival search yielded a direct match. The documentation proved definitively that the 3 recovered weapons were issued to and installed in a Yakovlev Yak-1 fighter bearing the operational serial number 1342. That archival lock resolved the frame number contradiction and allowed serial number 1342 to be traced through regimental records. The aircraft is reported as having flown first with the 423 Fighter Regiment connected to Moscow and later Gorkij air defense duties, before serving with the 485 Fighter Regiment under Major G.V. Zimin. That sequence places the aircraft within the broader Demyansk fighting, while the weapon number match remains the strongest identification anchor. Securing this identity is the foundation of any museum restoration. Without a verified serial number, a recovered airframe is merely a collection of salvaged parts. With a locked identity, it becomes a distinct historical artifact with a traceable operational lifespan. The archival triangulation converted an anonymous wreck into a documented machine. The historical gap was closed, but the engineering reality of the physical artifact now dictated the next phase of the operation. The long immersion in the lake had profoundly altered the material composition of the fighter. With the identity proven, how much of the physical structure could actually survive the transition from water back to air? The transition from an aquatic environment back to a dry hangar forced a severe engineering trade-off between the aircraft's surviving structural zones. The aircraft was built utilizing a mixed material construction method, a common production standard during its manufacture in 1941. The central core of the aircraft is a complex framework of welded steel tubing. This metal cage encompasses the cockpit, the engine mounts, and the primary structural spine. Because this steel frame had spent decades in cold fresh water rather than warm salt water, much of the airframe and equipment could be considered recoverable after cleaning, stabilization, and inspection. The outer extremities of the aircraft, however, presented an absolute failure condition. The wings and the tail-flying surfaces of the fighter were manufactured almost entirely from wood. These structural sections were bonded together using the organic glues available during the early 1940s. This specific combination created a severe operational vulnerability defined by composite degradation. Over the decades of total immersion, the cellular structure of the timber became completely saturated with lake water. More critically, the water chemically dissolved the organic adhesives holding the laminations together. Upon extraction from the lakebed, the wooden wing structure was not just waterlogged, it had delaminated badly enough to be treated as structurally unairworthy. The primary load-bearing joints could no longer be trusted to carry flight loads. The wings were essentially a collection of loose, warped timber held in their general geometric shape only by surviving metal brackets and the decaying external skin. Moving or supporting this degraded wooden structure in a dry hangar environment created an immediate handling hazard. As water evaporated, the timber could warp, shrink, and fragment uncontrollably. Since the failed glue joints inside the main spars could not be reversed, the wing and tail assemblies had to be replaced with newly manufactured wooden structures built to the exact original specifications. However, simply bolting a replica wing onto the original steel fuselage would sever the historical integrity of the aircraft. To prevent breaking the story of the airframe, the restoration team executed a meticulous protocol of provenance transfer. While the bulk wooden spars and ribs were functionally useless, the surviving metal fittings inside that wood were highly valuable. These reusable brackets, hinges, control fittings, and landing gear-related hardware were the true mechanical joints of the aircraft, the parts that could carry provenance into the rebuilt structure. Technicians carefully mapped and extracted every surviving metal fitting from the disintegrating timber, avoiding bends, stress, or distortion as the brackets came free from the warped wood. After cleaning and non-destructive testing for microscopic fractures, the engineers fabricated a new wooden wing structure around those exact surviving fittings. That integration secured the airframe provenance while clearing the way for the next mechanical question: the condition of the submerged power plant. When technicians opened the forward cowling, they expected to find a solid block of oxidized iron. Instead, they found a mechanical core wrapped in the dissolved remains of the outer casing. The Klimoff M105PI-12 engine was manufactured using a highly specific material profile dictated by strict aviation weight limits. To maximize the thrust-to-weight ratio of the aircraft, the engine used lightweight magnesium alloy castings among its casing and accessory components, while heavy internal power components, including the crankshaft, connecting rods, and cylinder liners, were made from high-strength steel. Once the aircraft settled on the lakebed, that material profile began to matter. Over decades in cold, low oxygen freshwater, the external magnesium casings degraded and left sections of the steel internal architecture exposed. The result is best described cautiously as sacrificial anode behavior rather than absolute chemistry. In a shared electrolyte, the more active magnesium could corrode preferentially while the less active steel was comparatively protected, assisted by cold freshwater, low corrosion rates, and oil trapped inside parts of the engine. The forensic results of this chemical exchange were visible on the teardown bench. When restoration engineers dismantled the remaining engine structure, the heavy steel internals were reported in remarkable condition, with no significant corrosion described in the available restoration account. Even the oil inside the engine was reported as clean and fresh. The preservation scale extended beyond the engine block itself. Investigators also recovered ammunition-related components and ammunition dated 1940, evidence that required specialist handling and deactivation rather than dramatic treatment as usable ordnance. These findings showed preservation but not full operational completeness. Despite this preservation of the core, the physical loss of the magnesium casings created a severe operational limit. A liquid-cooled aviation engine cannot function without a sealed external block to contain the pressurized oil and the coolant fluids under high thermal loads. Furthermore, the engine block acts as the primary load-bearing structure, mounting the entire heavy power plant directly to the steel fuselage frame. The original casing was functionally destroyed, rendering the engine structurally useless in its present state. To move toward operational status, the engineering team sourced an additional engine from the Musée de l'Air in Paris through an exchange while assessing the original engine for recoverable parts. The later restoration account reports that the Klimoff 512 engine was overhauled and run on a test rig, but the available public evidence does not prove a complete transplant of the original steel core into a donor block. The exact historical engine material therefore has to be described cautiously. Recoverable original elements mattered, but replacement material was also part of any practical rebuild. How would those limits shape the final objective of the restoration? The condition of the salvaged components forced the final operational pivot. Because original metal fittings had been integrated into new wooden structures and the steel fuselage spine remained fundamentally sound, an airworthy restoration was mechanically conceivable rather than merely cosmetic. In 1991, the aircraft was acquired by the Historic Aircraft Collection, and restoration started soon after. The objective was to restore the airframe to original specifications with an airworthy outcome in mind, though the available public evidence supports this as an intended goal rather than proof that the aircraft had already returned to flight. That objective shifted the work from preservation toward certification, documentation, and structural proof. Any move toward flight required inspection, repair documentation, and regulatory approval, with critical welds, joints, and bearing surfaces examined and repaired to accepted aviation standards. The restored engine, containing the surviving original steel internals preserved by the lake water, had to be mounted and precisely aligned. The engineering team was required to ensure the thrust vector, the fluid containment systems, and the overall center of gravity matched the original factory specifications perfectly. Throughout this rigorous industrial overhaul, the core historical identity of the aircraft remained the central anchor of the operation. The machine was not being rebuilt as a generic representation of a wartime fighter. It was historically identified as serial number 1342, while its United Kingdom civil registration was G-BTZD. The restoration logic now centered on mechanical fidelity. Every component added to the airframe, from the newly manufactured wooden wings to the replumbed coolant lines, was mathematically calculated to preserve the original aerodynamic profile and weight distribution. The flight control cables routing through the salvaged 1941 pulleys had to operate without binding under heavy, positive aerodynamic loads. The engineers had to document every single torque value on the newly fabricated wing, attach points to satisfy the modern flight regulators. Integrating salvaged 1941 material into a project aimed at flight was the most ambitious conclusion of the recovery. A static display would have preserved the aircraft's shape. This restoration aimed to preserve its mechanical logic within the limits of documented evidence and modern regulation. The result was not an overclaim of untouched originality, but a verified identity, recoverable original material, and a rebuilt structure organized around the possibility of regulated flight.